Hey guys, welcome to your third lesson in Unit 8, where we're going to really pull in everything we've learned in the past few units and put it in with electrochemistry. So we're going to be talking about the cell potential and then how that's affected by shifts in order to get to equilibrium. And we're going to throw in Gibbs free energy, so that thermodynamic favorability or non-favorability, so this idea of it being spontaneous or not spontaneous. So first of all, up until this point, I want you to make sure you realize that we have been looking at cells that were at standard conditions. And standard conditions mean that the aqueous solutions were 1 molar. So up until this point, all of our solutions have been at 1 molar. So what we're going to do here is we're going to look at, okay, well, what if they weren't at 1 molar? What if our concentrations were different? We're going to apply Le Chatelier's principle, which we learned way back when in Unit 3. All right, so we have a redox reaction, right? I've given you this one here. So if I increase the concentration of cesium 4+, well, if I look at my equation, cesium 4+ is a reactant. So if I increase a reactant, I shift right. Well, by shifting right, I am driving this redox reaction. I'm driving the electrons over to do the reduction. So that is going to increase the cell potential. Now, if I were to increase the concentration of either of the products, in this case, I can increase either because they're both aqueous. But if one of them was solid, remember, we can't change the concentration of the solids. It's only aqueous solutions that we can change the concentration of. But if I increase the concentration of the product, well, I shift left, which is going to work against the transfer of those electrons. And so that's going to decrease the cell potential. So let's look at this example. We've got aluminum and manganese, and the standard cell potential is 0.48 volts. So that's when both solutions are at 1 molar. Now let's look at these two situations. The first, we have upped the aluminum concentration to 2 molar. Well, what happens when we increase a product? We shift left. And so in this case, we are going to decrease, or we're going to have a smaller cell potential. Now in B, we are increasing the concentration of the manganese solution, which is in the reactants. So when I increase the reactant, I shift right, which for a redox reaction in a galvanic cell is going to increase the cell potential. So I'm going to have a larger cell potential. So we're just applying Le Chatelier's principle here. So the key thing we got to look at is, are my reactant concentrations larger or my product concentrations larger? Now, we can take the same principle and we can actually use the exact same reaction, same metal, and same solution. So in this example, both of them are silver. Both of them are in silver chloride solution. But what we can do is we can alter the concentration. And so instead of it being the difference in reduction potential, which normally, we have two separate reactions, and the one with the higher reduction potential is the one that's going to be reduced. So instead of that spontaneous reaction happening because the one thing has the higher reduction potential, now it's the difference in concentration that's going to be the driving force that's going to pull the electrons. So the electrons are going to flow from the thing with lower concentration to the thing with higher concentration, and we call that a concentration cell. So the difference here is, instead of having two different half reactions, we have the same half reaction, but we're altering the concentrations to be different to actually cause the reaction to occur. So we have this equation. You will find it on your reference sheet. It is called the Nernst equation. And what it does is it actually gives us a way to numerically calculate how a change in concentration will change the cell potential. Okay? So we have, notice that here we don't have the degree sign. That means that it's the cell potential not at standard conditions, so not at 1 molar. And that is calculated by taking the standard cell potential minus RT over NF times the natural log of Q. Wait, what is all of that? Well, remember, Q is the reaction quotient, which we calculate just like K, so products over reactants raised to their coefficients. A lot of times for these, we're only going to have one product and one reactant, but you do have to make sure you balance your equations because you could have a coefficient. R is the gas constant. We're dealing with energy here, so it's the one with joules, 8.314 joules per mole Kelvin. F is Faraday's constant. It's how many coulombs of charge there are per mole of electron. So 96,485 coulombs. That's, of course, given to you on your reference sheet. And then N is the total number of moles of electrons being transferred. So if we have 2 electrons, then that number N would be 2. Now, sometimes you'll see the Nernst equation written like I have it here. And what that is most of the reactions, most of the time, we're going to be doing them at standard temperature, which is 25 degrees Celsius or 298. So if we take this right here and we do the gas constant, which is going to be the same for no matter what, and then we plug in 298 Kelvin divided by Faraday's constant, that equals 0.0257. So what that does is it just takes out some numbers for us. It just takes this and plugs in what that equals. So it's kind of like how we say 1 mole is 22.4 liters when we're at STP, and so then we just use that number, but any other time we actually have to plug things in. So if we were at a different temperature, we would have to plug it in, but most of the time we're going to be at 298 Kelvin, and so if you want, you can just use this number as just less to write down. But what's given on your reference sheet is this, and so you can always use this. You can always plug in the 8.314, 298, and the F along with and the number of electrons. So let's think about this in general before we actually get to numbers, okay? So in general, let's think about if Q is greater than 1. So in other words, if Q is greater than 1, we have more products. The product concentration is larger, okay? If that number is above 1, then the natural log of it is going to be a positive number, okay? So if we take the cell potential and subtract a positive number, the cell potential is going to go down, all right? If we have a Q less than 1, meaning we have more reactant, then we plug in a number less than 1 for Q. Natural log of a number less than 1 is negative. So if we do the cell potential minus a negative, we end up adding to the cell potential. And so the cell potential is going to increase. So you could have a question that just asks you, instead of actually to calculate it, it might just say, will the cell potential increase or decrease? Explain. And you can say, because Q is greater than 1, it will decrease. And so that's using the Nernst equation to figure that out. All right, guys, so let's look at this example. So we have a galvanic cell based on the reaction of aluminum and manganese. And manganese is being reduced, aluminum is being oxidized. Now, if we were given the standard reduction potentials for each of those half reactions, we could calculate the standard cell potential. In this particular problem, we are given the standard cell potential, and we're told it's 0.48. So that means that standard cell potential is 0.48. So that's when they're at 1 molar, remember. So we're told manganese this time is at 0.5 molar and aluminum is at 1.5 molar. So we already said we have our standard cell potentials. Remember, our equation is not at standard cell potential equals the standard cell potential minus RT in F natural log of Q. Because we're not given a different temperature, we are at we're at room temperature standard, so we can plug in the 0.0257 for the RTF. All right, so now we got to calculate Q. So products over reactants, so aluminum's concentration squared over manganese's cubed gives us 18. And then we have to consider how many electrons are actually being transferred. So every aluminum has 3, but we have 2 of them, so that's 6. Every manganese has 2, we have 3 of them, that's 6. That's why we have these coefficients here, because we have to be balanced. So N is 6 here. So now I plug all of that in, the standard minus 0.0257, that's standing in for that RT over F, divided by N, which is 6, times the natural log of 18 gives me 0.47. Now, if we look, we see here that our products were greater than our reactants. So what we expected was for the cell potential to decrease. And even though it's very slightly, it did decrease when compared to the standard. All right, so here we're given a cell in line notation, and it's actually a cell constructed with just zinc. So zinc is our anode and our cathode here, but the solutions have different concentrations. And so that's what makes it a concentration cell. Now, we got to think about in line notation, what's in our reactants and what is in our product. So remember that for line notation, it's anode on the left and cathode on the right. Okay, so that means that our reactants are here, and then our products are here. Okay, so whenever we're calculating Q, we have to think about that because we got to do products over reactants. Okay, so our equation, cell potential not at standard conditions, is the standard cell condition. I'm going to use the 0.0257 because we are not given an alternate temperature, so we assume that it's standard temperature, which is 298. All right, the first thing I need to do is calculate my standard cell potential. Well, since this is zinc and zinc, then negative 0.76 minus negative 0.76 is, of course, 0. So that's why if the concentrations were the same, this would not actually have any sort of voltage. So the standard cell potential is 0. N is the number of electrons, so in this case it is 2. And then Q is products over reactants, so my product is 0.1 divided by my reactant, which is 0.5. We get 0.2. So now I'm going to plug that into my equation. So I have 0 minus 0.0257 over 2 times the natural log of 0.2, and I get 0.021 volts. And if we look, our reactants were higher than our products, so we expected this to shift right, which would increase the voltage, and it did. All right, so let's look at this example. Here we're given aluminum and copper, so it's not like the previous example where it was the same metal. We're asked to calculate the cell potential, so our concentrations given are not at 1 molar, so we are going to have to use our Nernst equation. Now, remember again, reactant, reactant, product, product. Okay, so first thing I'm going to do is calculate my standard cell potential. 0.34 reduction minus oxidation, or we can think of it as anode and cathode. So cathode minus anode, so copper minus aluminum, we get 2 volts. Right, now we have to figure out our total number of electrons. Well, I see I have 3 in the aluminum reaction, I have 2 in the copper reaction. So I'm going to multiply the top by 2 and the bottom by 3, and that's going to give me 6 electrons total. Now, when we go to calculate Q, we have to use our coefficients, so I need to write out my balanced equation. Now remember, the lower reduction potential is going to flip because it's running as the oxidation. So that matches what we set up here. Solid aluminum is the reactant, aluminum 3+ is the product, it's being oxidized. And on the bottom, we have the reduction of copper. Of course, my electrons cancel. 2 aluminum plus 3 copper 2+ yields 2 aluminum 3+ plus 3 copper. So when I'm calculating Q, products over reactants, aluminum 0.15 squared over copper 0.025 cubed, and that gives me that Q equals 1,400. So there's my 3 values that I have to calculate to plug into my Nernst equation. So the standard potential minus 0.0257 over 6 natural log of 1400. Again, I'm using this because I'm not given an alternate temperature, so I have to assume that I'm at standard temperature. So when I do that math, I get 1.97 volts, which it decreased, which is what I expected because my products were higher than my reactants. So with our Nernst equation, we are calculating the maximum cell potential before any current flows. Because as our current flows, electrons are transferred, our concentrations are going to change. And eventually, this is going to reach equilibrium. And now remember, at equilibrium, Q is equal to K. So then the cell potential is 0 and delta G is 0. We'll get into talking about delta G in a minute. That explains why a battery is dead. Okay, so this is going to occur until we get to equilibrium. So what that means, so we know that at equilibrium, Q equals K, and the cell potential is 0. I can plug in 0 and K in the Nernst equation, and that gives me a way to calculate the equilibrium constant. So over here, I have it just solved. I added this to the other side, and then I divided to get this version, or this is using that standard temperature. Okay, so I'm given this example. I have this redox reaction. I have my 2 half reactions with their standard cell potentials. Now, the first thing I got to do is I got to balance the equation. So that's why I have this 2 right here. That gives me 2 sulfurs on both, or 4 sulfurs on both sides and 6 oxygens on both sides. On the bottom, we have 1 chromium and 1 chromium, but we got to multiply the bottom through by 2 so that our electrons will cancel. So that gives us 2, 2, and 2 up here. So now my standard cell potential is going to be 0.17 minus negative 0.5. Sorry about that. Gives me 0.67 volts. Okay, so that's my standard potential. So now I can use that to calculate K. So I'm going to plug in natural log of K is equal to N is 2 times the standard 0.67 over 0.0257, 2 times 0.67 divided by 0.0257 gives me that the natural log of K is equal to 52.14. So I got to raise the natural log e to both sides, and I get that K equals 4.4 times 10 to the 22nd. So if we are at equilibrium, we can use the Nernst equation to actually calculate the equilibrium constant. All right, so here is our last equation for these set of notes, and we are given delta G, standard free energy, is equal to negative NFE. So N is the number of moles of electrons, E, of course, our cell potential, and F is that Faraday's constant again. And so this is also given to you on your reference sheet. So here's where we're kind of taking everything full circle. We've related the cell potential to equilibrium and the equilibrium constant, and now we're relating it to free energy. So the max cell potential is directly related to the free energy difference between reactants and products. So think about this. Look at this equation. If I have a positive cell potential, that gives me a negative delta G, and that is spontaneous. If I have a negative cell potential, that will give me a positive delta G, and so that would be non-spontaneous. So now we have another way to indicate whether it's spontaneous or not spontaneous. All right, so let's use this equation in an example. So it says, using standard reduction potentials, calculate the delta G for this reaction, and then is it spontaneous? So here we're given our standard potentials. Copper is being reduced, iron's being oxidized. So I can already bet you it's going to be spontaneous because the higher reduction potential is the one being reduced. But we calculate the standard cell voltage, it's 0.78, so a positive standard cell voltage indicates spontaneous. And then our number of moles are 2. Moles of electron is 2. So then we plug in Faraday's constant, the standard, 2 moles, and I get negative 1.5 times 10 to the 5th joules. So we can say, in fact, that yes, this is spontaneous. We have a negative delta G. We have a positive cell voltage. Okay, so the question here tells me to find if this is spontaneous. First thing I notice is that we are not at 1 molar. So this is not the standard voltage. So we're going to actually have to use the Nernst equation to determine the actual cell voltage for this cell. So first I have to find the standard. Remember, we always do reduction minus oxidation. So let me look at my equation. Cobalt is being oxidized and iron is being reduced. So iron minus cobalt gives me 0.44 minus 0.28, which gives me negative 0.16. So at standard conditions, this is not going to be spontaneous because we have a negative cell potential, but we're not at standard conditions. So next, I have to calculate Q, products over reactants, raise their coefficients. So 0.15 divided by 1.94 gives me 0.077. So now cell potential is equal to the standard minus 0.0257 room temperature over N electron numbers, 2 times the natural log of 0.077. Let me do this math. I get negative 0.16 volts minus negative 0.033. So that gives me negative 0.127. Now, it did increase the voltage. It's less negative now, which we expected because our reactants are higher than our products, so it is going to shift it right, but it is still non-spontaneous because of the negative cell voltage. Now, if the question asked me to justify if it was spontaneous or not by calculating delta G, then we can also do that. We're going to have negative 2 times Faraday's constant, 96485, times my cell potential. And we see here that double negative is why I'm going to have a positive delta G value. And I get positive 24,507 joules. So this is non-spontaneous for both reasons. Okay, so here what I've given you is a diagram that relates delta G to the equilibrium constant to cell potential. So this was the free energy equation we looked at last unit that relates free energy and the equilibrium constant. This is the equation we just worked with that relates the free energy to cell potential. And then this equation is the Nernst equation. So that's the Nernst equation. This is what's given on your reference sheet. But remember, if we're at equilibrium, Q equals K, so I pop K in there, and the cell potential is 0. So this is just the Nernst equation solved at equilibrium. And so it was what combines cell potential with the equilibrium constant. All right, so this question says, what is the standard free energy change and the equilibrium constant for the following reaction at 25 degrees Celsius? So 25 degrees Celsius, that is our 298 Kelvin, so that's our room temperature or our standard temperature. So the first thing that I have to calculate here is my standard cell potential because I need that to find my free energy. So I have silver being reduced here. So I got to do silver minus iron. So I've got 1.24 volts is my standard cell potential. Now it asks me for free energy change, that's delta G. So my equation, delta G, negative N F E. Negative N is the number of electrons. So I look here, I'm going to multiply this one through by 2. That's going to cancel out my electrons. So N is 2 times Faraday's constant times the cell potential. And that gives me a delta G value of negative 239,282 joules or negative 239 kilojoules. So remember, oftentimes we have it in kilojoules because the numbers are so large. So With negative delta G, this is definitely a spontaneous reaction. We expected that. Higher reduction potential is being reduced, and we have a positive cell voltage. All right, now we're going to find the equilibrium constant. So the way we can calculate the equilibrium constant, we actually have two options here. Now that we have the free energy, we can use that delta G is equal to negative RT natural log of K. That's given on your equation sheet. Or we can use the Nernst equation solved for equilibrium. We can do either one, okay? So let's solve it first with this equation here. So I'm going to use my joules because R is in joules, or I could change R to kilojoules, up to you. My temperature is 298 times the natural log of K. So now I have negative 8.314 times 298, negative 239.282 divided by that answer. You get 96.6 is equal to the natural log of K. That is E to both. And I get that K equals 0.8 times 10 to the 41. Massive equilibrium constant. All of this is pointing towards the fact that this is a product favored spontaneous reaction. Now, if we solve this over here with our other equation, we have the standard cell voltage is 1.24 volts equals, this is at standard temperature, so I can use the 0.0257. N is 2 times the natural log of K. And so then I have 0.0257 divided by 2, 1.24 divided by that answer is 96.5 equals the natural log of K, and looky there, we get the exact same answer. We get 8.1 times 10 to the 41st, but close enough. So you can use either of those equations. You're going to get the exact same equilibrium constant. Really just depends on what you're given and what you've already calculated. Okay, let's do this final question. So same thing. We are looking for the standard free energy change and the equilibrium constant. We're at standard temperature and we're at standard concentrations because I'm not told otherwise. So the first thing I'm going to do is I'm going to calculate my standard cell potential. So copper is the one being reduced. So 0.34 minus negative 0.14 equals 0.48. So then delta G equals negative NFE. Negative N is 2 because it's 2 electrons times Faraday's constant times the cell voltage, and I get 92,625 joules. And then my K value negative 92,000. So that's using the equation delta G equals negative RT natural log of K. And I get that K equals 1.7 times 10 to the 16th. Again, we can use the standard cell potential equals 0.0257 over n times the natural log of k. And as expected, we are going to get the exact same answer. So it does not matter. I'm not going to ever ask you. AP is never going to ask you to use both of them. I'm just showing you both to show you can use either one and you'll get the correct answer with either one. Okay, guys, that was a lot. If you listened to the entire thing, then you can send me a message that says, "We love Gibbs Free Energy." All right, y'all. See you next time.